Yeah, thanks, boss. So I will be talking about isotopes and geochronology. I just wanted to mention, though, you know, it was great to see so many people at the Women in Mining and the student night last night. And with that in mind, it's great to see so many of you here at 9 to enjoy my talk about isotopes. There's a lot of names on this slide as well, so I just want to say, like, nothing I do in isolation. There's always a cast of quite a few people involved, and these are not everybody. I'm sure there are people missing. So with that said, let's jump right in to everyone's favourite topic, isotopes. First of all, we'll just get some data up here. We'll maybe put a sneeze plot up, a few more plots, some equations. All of which to say is, I think that isotope geochemistry has a bit of an image problem in mining and exploration. The rest of my talk, I'm going to be telling you why I think that is and what we're doing to try and address these issues. So just to start us off on a fairly stable base of understanding, I'm going to explain a bit about isotope geochemistry. Every element in the periodic table has at least one isotope, so there are lots of them, and I don't have time to talk about them one by one, and you'll be pleased to know I'm not about to try. With that also in mind, I need to kind of refine the scope, and in this talk I'll mainly be focusing on the radiogenic isotope that we use for geochemistry and geochronology. Keeping in mind that yesterday we heard some talks about the oxygen and sulfur as examples of other isotope systems. So to understand radiogenic isotopes, you need to understand two concepts, both of which you should be familiar with if you work in geoscience or have done some amount of science at uni. The first is the idea that the Earth is composed of different reservoirs: the core, the mantle, the crust, the hydrosphere, the biosphere, the atmosphere. And as material moves through these different reservoirs, it doesn't all move uniformly. Different elements move through these reservoirs depending on the chemistry and these are the things that all geochemistry really is looking at. How these elements move through these reservoirs, and what that tells us, in our case, about how mineral deposits form. So, I want to make it clear, even though we're talking about isotopes, in the case of radiogenic isotopes, it really still is about chemistry. Some of the lighter isotopes, like oxygen and whatnot, they do have isotopic differentiation because that's a different property. The second fundamental a concept we need to know is that of radioactive decay. So not only do these elements partition into different reservoirs, some of these elements are parent-daughter pairs that undergo radioactive decay. And so it's not just these this material moves into different reservoirs. When it's in there, it's also still changing composition through time based on the radioactive decay. So it's this property of time that comes into the radiogenic isotopes that is what makes them, to me anyway, so interesting. So yeah, I've just got some examples there as well. You know, when we're talking about things that we can understand with the isotopes, and often geochemistry more broadly, formation of new crust, and addition of new material from the mantle to the crust, and the origin of fluids that can generate ore deposits. All these things we can track and trace with this kind of work. And there's a picture there just to give you another, concept. So, as material moves from the mantle to the crust and where it resides in the crust before it gets maybe erupted or placed at shallower levels, all that can be in some ways measured and tracked and used to generate ideas about how the Earth's been changing and forming through time. I did want to just talk a little bit about bringing geochronology in as well. That's the part that most people will be more familiar with, dating rocks. Great. So the radiogenic geochronology and the radiogenic isotope geochemistry, two sides of the same coin, same isotopes. So if you find that some of these concepts get a bit blurred, it's because they are sometimes by nature actually blurred. So in the case of uranium, lead, it's the same decay. It's the same elements. It's the same isotopes, but we're focusing on different components of those elements to understand different parts. So, as said there, geochronology gives you the age, and isotope geochemistry tends to give you time-calibrated geochemical data. Yeah, hopefully that gives you a little bit of a update. So what? Who cares? This is the classic problem we have. Deposits are hard to find, particularly as we explore undercover. Geophysics has for a long time been the backbone of exploration. We've seen how well it works. It is just to say here, it is a snapshot of the Earth as it exists today, right now. Isotopes do have that time component which lets you draw back through time, which makes it, some people call it paleogeophysics. So that gives you kind of some sort of concept of what we're talking about. But the overall message is that we need a diversity of tools and approaches to apply to different scenarios to increase the chances that we'll make more discoveries. And I do think isotope geochemistry and geochronology fits into these array of tools that should be available to people. So there are different ways to apply geochronology and isotopes to mineral prospectivity. The basics, you date your deposit, you find out the age, you go look for things that are the same age. Makes sense, and that's great, it's fantastic. Similarly with isotope science, you can find the isotopic character of your deposit, and then you can go look for similar isotope characteristics. It's a little more complicated because there's a bit more going on in that, but that's kind of an empirical approach. There's also a more conceptual approach where you try to understand, use isotopes to understand favourable tectonic ingredients that go into making deposits. You're reconstructing the tectonic history to get a more, holistic impression of the Earth, to then predict favourable times and places for undiscovered deposits to occur without necessarily directly referring to the discovered ones themselves. So isotopes can help you. The picture on the left, I think, is probably too small for people to read, but, it's the basic idea of, different tectonic settings actually do result in different isotopic differences, which can really inform on where you are in a setting. And it's particularly useful when the setting no longer looks like this, when it's been cut up, disjointed, and it's very hard to interpret other ways. So here's another diagram. It's been around for a bit now. This is the minerals, a diagram showing mineral systems model, and basically the concept of this is that things that create mineral deposits operate over a huge range of spatial scales and also a huge range of time scales. So, if you're starting, with huge processes such as crustal differentiation, the formation of cratons and huge crustal blocks, that kind of thing, those big picture scenarios have implications for deposits. And then, as you focus in, you have enrichment of metals through geodynamic and tectonic processes, focusing fluid flow, directing it all the way through to at the really tiny scale that we're talking about relative to the size of the whole Earth, the mineral deposit at the end, which, and all the way through, there are processes that occur that make it likely or less likely for a deposit to form in a certain time, place, that kind of thing. And I wanted to point out that isotopes can help at most of these scales, along, of course, with other techniques. So here's the next slide is an example. It's a classic. This is a craton scale example. This is the Neodymium isotope map of Australia by Dave Champion in 2013. This is an example of the isotope geochemistry side of things with the time component front and centre. So the colours represent a proxy for kind of the age of the crust, not the age of the rocks, but the age of the crust that formed the rocks. So makes sense, I hope, with what you understand about Australia, you know, old in the west, young in the east. There are little bits and pieces to pick apart as you look in detail, you know, so you've got these big cratonic blocks, and then in between you have these areas of younger material as these blocks get fused together, that kind of thing. Yes, and to bring it back to mineralization, I apologise that this is on the wrong side of the continent for us, and also probably the wrong end of the time scale, but it's a really neat example of the relationship between isotopic data and mineralization. So here we're talking about nickel mineralization. This is the Yilgarn craton that you see over in Western Australia. What you see on the map is isotope data. Again, this is neodymium model ages. The colour scheme is the greens in the east are younger, the yellows and reds in the west are older, and over the top of here, the triangles are nickel deposits, and the larger the triangle, the larger the deposit. So because the nickel here is hosted in mantle rocks, komatiites, there is a strong relationship between kind of mantle influence and whether or not you're going to get a nickel deposit. And so the nickel here is kind of along, a lot of it is along this, it's not actually associated necessarily with one or the other particular model age, it's actually along this line of difference or gradient in the isotopes. So the concept with this is that these two isotopic blocks have some sort of lithosphere scale weakness that allows mantle-derived fluids to more easily access near surface. And so that's an important concept as well when you're looking at isotopes. It's not always in fact, it's often not the absolute value of the isotopic data. It's often the differences and the gradients and that kind of thing. But all to say that at this scale, you can still use isotopes to predict likely locations of undiscovered deposits. I'm going to switch over to a very local example now. This map is in the Zeehan field in Tasmania. There's a little location map down the bottom left. Zeehan has historical silver mining and current tin exploration, and there are many people in this audience who know more about it than me, so I'm not going to try and stay out of trouble and keep it general, but the map shows the surface geology. Let's see what we've got here. The light tans, colluvium, the browns, Una Formation, the blues are various groups, and then some ultramafics on the left. In red, there are the Comstock, Montana and Queen Hill mines or deposits. And then somewhere underneath there's the Heemskirk granite, which is thought to be associated with the mineralization. So all these little points on the map are lead isotope analyses to try and understand the influence of deep-seated units. So this next one shows the lead isotopes. This is just a lead ratio. It doesn't so much worry about the time component. This is more using these isotopes as as what you might understand as like a geochemical tracer. So I forgot to mention also that the contours that you see are the inferred depth to the buried granite, and the width, you're not going to be able to see the numbers, but it's shallower to the north and deeper to the south. And the lead isotopes look as such. So they're slightly higher to the north, slightly lower to the south. And separately, the Heemskerk granite has been isotopically characterised and found that it has higher lead. So the interpretation of this is that this is the lead isotopes are reflecting the influence of fluids associated with that granite in the region of the deposits, and then the influence is diminished as you move away. So in this way, it's a kind of a demonstration of how you might be able to use isotopes as a vector or a tracer, and definitely to understand the influence of geology that's not exposed to the surface, because these are surface samples in lead minerals, I believe, so we're not actually directly sampling that granite here, we're sampling the influence or the halo effect of it. I'm going to have to move a bit more quickly but I want to talk about, why, if isotopes are so great, why aren't we using them more? I think there's a few reasons for that. Data is hard to access. It's expensive if you want to get it yourself. It takes a fair amount of time to collect it. It's also quite hard to access other people's data. Anyone who's tried to put together like just geochemistry compilations know how difficult it is to unify everything, even to find it, particularly when it's across multiple parts of the literature. There's a high bar to entry for non-experts. I've tried to kind of give you the basics. I suspect there's more work to be done. It's just not, geochronology is fine. I think people understand that an age is an age and what it's useful for, but the isotope geochemistry stuff, it's not straightforward. But I will say I think there could be more done to make it a bit more accessible. And often we're missing the baseline data. When we detect anomalies in the deposits, well, what is the non-anomalous signal? How do we know when we're out in the non-prospective field? So this has big implications, in particular for discovery. So, I don't think there are as many discovery examples for isotope geochemistry as these techniques have the potential to deliver. I will say that I think part of that is isotope geochemistry does work well with others, and so often it can be integrated, and that's how we use it at GA, and I know GS New South Wales as well do that. So it's not going to be as, there aren't going to be as many stories about, drilled some magnetic anomaly. It's not going to be like that necessarily. But at the same time, I do think the above issues are also having an influence. So what's the plan? What does it look like? I just want to talk about geophysics as an example. This is a beautiful geophysical coverage across Australia, onshore and offshore, 2019. It's amazing, but and in general, you can look at that and understand what it is. But I asked Phil at GA to kind of give me a look behind the scenes, and he sent me a spreadsheet, some code, and this workflow. All of which to say is that it takes a lot of effort, a lot of hard work over decades to create these things. But it does show that you can create accessible geoscience if you work at it. And we've done the same with isotope geochemistry in some ways. Here's a neodymium map of Australia. Again, I really like this map. It translates some of the more complex isotopic information into more understandable concepts. I don't think that these kinds of maps are always the solution for isotope data, because you have 4 dimensions, X, Y, and depth and time, and you're trying to put it into 2 dimensions, but I do think it has its place and can be used more. So what are we doing? Here we go. I'm going to talk about the first 2. Data is hard to access and there's a high bar to entry. We have been working to compile and synthesize and make geochronology and isotope data more accessible to everybody, with a focus on people and minerals and exploration. And this is an ongoing process, but we've made huge strides. I do want to say at this point we're not the only people doing this. For example, Geological Survey of New South Wales have an excellent geochronology coverage, and that's why we're trying to incorporate that in with ours to have the best of both worlds. So you can download this data. and take it away, but we're also providing built-in tools, so you can like select a little area down here and do a quick time-space plot and mouse over things that you're interested in. So it's not just providing the data, it's also increasing accessibility. Similarly with neodymium and other isotopes, lead, and lutetium hafnium at the moment, the data's there and it's been kind of baseline normalized, brought back to the same frame of reference. This is a problem, but I'll try to smash through. I want to say, we have, one of the very new things we have is a new compilation with GSV for Victoria. It's available on the portal and whatnot. I don't have a lot of time to talk about this, unfortunately, but it's a huge compilation. It's probably the biggest coherent age compilation for Victoria now. It was a lot of effort, and I thank GSV for their contribution as well. And similarly for Tasmania, that's up and coming. It's not yet, but it's in the final throes of QA/QC. And again, it's going to be massive. And MRT have been, digging out their geochronology from all corners of what they know about, and it couldn't have done it without them either. And we've got a book coming out. This is about increasing knowledge. If you want to know more about specifically isotopes in economic geology, metallogenesis and exploration, this is the name of the book. David Houston, who's in the audience, is an editor. I wrote a chapter about hafnium. There's a lot of smart cookies in here. It's focused on exploration and minerals. So the topics are radiogenic isotopes for dating. So there's a little bit of uranium lead, but it's also focusing on some of those techniques that are specific to ore minerals, radiogenic isotopes, which is what I talked about, light stable isotopes and metallic stable isotopes. So if this talk wasn't enough, there's plenty more information coming soon this year probably. Baseline data sets. So I mentioned that there's a lead, when you do lead isotopes, for example, that's a good example, and you're looking for anomalies, it can be hard to know what is anomalous if you don't know what's normal. So we have embarked on this lead isotope map of Australia project. Jan Lieberman is our postdoc working in Curtin University with us, along with a lot of other collaborators. I'm going to have to skip through this, but the basic idea is that neodymium and hafnium talk about deep processes across mantle, whereas lead isotopes are more focused on fluid in the higher crust, we believe, and that kind of thing. So it's talking more about fluid flow, in particular fluids that can form mineralization. The map on the right is an lead isotope map in ores map. It's effectively an anomaly map because it's on these very pinprick deposits rather than the large-scale geology. So we want to make an equivalent of the broader geology that can be benchmarked to your new results. There's also, alongside the ore data, there's also a huge database of water lead and soil lead isotopes at GA. So if we get the basement rocks, we can start linking all these together and really using all of them to their full extent. As part of this, we're trying to understand, can lead isotopes be used for pathfinding, vectoring, understanding, exploring away from the deposit more clearly, and what are the barriers? Can you explore using lead isotopes in basement rocks, perhaps by looking at feldspars rather than the ore minerals themselves? And can you collect reliable data sets quicker and cheaper using the laser ablation methods rather than the classic ID-TIMS method? So those are the main things that we're focusing on. We have some results. It's still early days, even though there's 43 samples on this plot. At this point, I'll explain the scale that you can see. Mu is a ratio that is one of the isotopes of uranium over one of the isotopes of lead. The way I remember what mu means, high mu is high U, and everything that implies. The results so far make general geological sense. In the Staveley region, where there's arc rocks, the mu is lower U, so that, reflecting the arc nature of this. Mount Painter has a lot of uranium around it, and it's got the highest mu so far, so it's promising, it looks good. There's a lot more to go. There's a lot of geological gaps here. There's a lot of units that aren't represented, so there's more to do, and it's going to be a big project, but we knew that when we came into it, and it's exciting to see these results so far. Look, I'm out of time pretty much, but I am on the last slide, so I've made up some time. I just wanted to say I hope that you can see that what we're doing is making it a lot easier to access this data, which at least gives you the ability to load it up and play with it and see if it's useful for you, as well as providing materials that will hopefully help you access that kind of knowledge you need to understand and use isotopes. We're providing the baseline data sets, and what I hope to be talking about next time are more discovery examples where people have used isotopes front and centre in their work. So I have to say thank you to all of the geological surveys for their data custodianship and for their collaboration. It's a fantastic working relationship with all of them. It makes it so much easier. Thanks also to the isotope geochemists and geochronologists. Very little of this actual data is mine. It's from everywhere else, so thank you so much. I didn't mention it, I'm glad I put it there. All the links to all the isotope stuff are in the abstract volume. And if you are using isotopes, if you know of discovery examples or you have data you'd like to share with us, please get in touch. And that's it for me, thank you.